Thank you very much. Welcome to lecture number 10 in the course EEE 4221. This is one of the courses offered at the University of Zambia and the School of Engineering. And today we'll be looking at convolution of discrete signals, part 1. My name is Dr. Charles S. Bobovia. Convolution is a process by which an input signal x of n interacts with a linear time invariant system to produce an output. This interaction is through a signal called h of n, which is basically when the two signals interact, the input x of n and h of n, they produce an output y of n, and that's basically what convolution is. Now, there are two types of convolution. The first one is linear, the second one is circular convolution. Usually, linear convolution deals with non-periodic signals, two signals that are non-periodic when they interact to produce an output. Basically, that is what is linear convolution. In circular convolution, basically, you have two signals, x of n and h of n. They interact in a system. That's a linear time invariant system, and then they produce basically output y of n, and it's usually best for periodic signals. Now, let's define what linear convolution is mathematically. Mathematically, linear convolution is basically where you have two signals, x of n and h of n, basically interacting in a linear time invariant system to leave an output y of n. So mathematically, if you look at equation 1 here, you will notice that you have the output y of n, put it here, output y of n equal to the product, convolution product of x of n and h of n. So the two signals here interacting, and they are producing an output y of n, and this is also equal to summation of x of k, where k runs from negative infinite to positive infinite, or this signal is being multiplied by h of n minus k. Again, k will run from negative infinite to positive infinite, and that's from the definition, though practically most signals will run from k equals 0 to some value, say k equals 5 or k equals to 8 and so on. So equation 1 here forms the basis of the definition of convolution, and we'll be using this method, this equation rather, in trying to resolve convolution of two signals, x of n and h of n. Now, I want us to move further by looking at the methods of resolving problems in linear convolution. Remember, I said there are two types of convolution. There's linear and circular. Let's begin with linear, and under linear, we'll look at three methods of resolving problems in convolution of discrete time signals. Okay, so the three methods include analytical method, the tabular method, the Z-transform method. In the next slides, we'll basically be looking at each of these methods in a bit of some detail. Let's begin with the analytical method. This is a method based on the formula, which we basically defined in equation 1. And to understand this method, let's do an example. Suppose we are to find the convolution of two signals, x of n equals 3, 1, and 2, and h of n, 3, 2, and 1. Now you notice that in resolving this problem, you need to understand that in the sequence x of n, the 3 here is basically at position, x of 0. Okay. And the next one here will be at position x of 1. And then the last one here will be at position x of 2. It's very important to remember. Equally, under the second signal, it's important to notice that this will be at position h of 0. And then the 2 here will be at the position h of 1. Okay. And then this one here will be at a position h of 2. So at any instance, the maximum value you get for x of n will be 1 at position x of 2, and then the maximum you can get for the second signal h of n will be the 1 at position h of 2. These positions are very important because as we do the convolution using analytical method, knowing these positions will help in determining the final solution. So let's look at this solution in a bit of a detail. The next slide here, what you notice is that I've picked again from the definition of convolution. Y of n is equal to x of n being convolved with h of n, and using the summation symbol from the definition, this is nothing but a summation of x of k, n minus k, where k runs from negative infinite to positive infinite. And this can be further broken, into the next equation here, where k is equal to 0. As you've seen, all our sequences are not starting from negative infinite; they are all starting from 0. So k will run from 0 to n minus 1, where n here, the capital N here, is basically, the highest number in the sequence, minus 1. And in this case, you're going to get, for example, if you look at the examples given, you notice that x of n was running from, so if x of n in this case is 3, 1 and 2, okay. So in that case, that means is that our k, our capital N in this case, our capital N will be basically these plus 1, with the number of sequences given here plus 1, which means you have 4 minus 1 here giving 3, and then that's your maximum value for k. And then we can now expand this equation, x of k, by putting k equals to, by putting k equals 0. So if we put k equals 0, then you're going to have x of 0 here. And then if we put a 0 here, then this one will simply be h of n. In the second term, when we put k equals 1, you put everywhere here, you put 1, 1, then you're going to have x of 1, h n minus 1. Then in the next term, we put k equals 2, then that would be x of 2, h minus 2, plus when we put k equals 3 there, then that will be x of 3, h minus n minus 3, so the sequence goes on. So having written this, our final goal is basically to get y of n. What will be the final value for y of n? So to do this, what we're going to do in the next slide is basically to substitute, starting, you notice in this equation, n is also changing now. For n equals 0, what will be the value for n equals 1, for n equals 2, and for n equals 3. So basically what we do here in the next slide, for n equals 0, let's put wherever we have n, we put a 0. So we put a 0 here, we put a, we put a 0 here, we put a 0 here. Then we're going to get x of 0. Wherever we have n, we had n here, we put a 0, this will be -2, -1. This tends to -2 and -3. Now, the next step is then we notice that in the sequence, we did not have h of -1. So all these h of -1, h -2 are not in the second signal h of n. Therefore, it means these are non-existent, they are basically 0. So anything multiplied by 0, all these terms here will give us a 0 up to there. So these will give zeros because you have negative h values, which are not in the original n of h equation. So that means that the only possible combination there is x of 0, h of 0. And we know that x of 0 is 3 here, x of 0 is 3, h of 0 is 3. So when we multiply these, we get the first product 9. Then we move on again in this in the equation. We move on by substituting wherever we have y of n. In this equation here, we substitute n equals 1. So if we put 1 here, basically what we are doing here is putting a 1 here. If we put a 1 there, wherever there's n, we put a 1. We put a 1 here, this will be 0. And then we put a 1 there, we substitute everywhere there's n for 1. Then you end up with the equation as shown in the next slide. Basically, you end up with the second equation here. So whenever we put y of n, put 1 there, we put 1 there. When we put 1, then this will become h of 0. Then the rest here will become negative. Again, each of these negative components will not account for the final solution. The final solution will basically be based by these two here. And again, x of 0 is 3, h of 1 is 2, plus x of 1 is 1, h of 0 is 3. When you multiply and add the 2, you get the 9. In the third scenario, you have n, you equate n for 2. So you have y of 2 there. And then here, this becomes 2. Then this becomes 2 minus 1, which is h of 1. Then this becomes h of 0. Again, this term here will not count because of the negative 1 there. So the final product will have that term and this term, and basically 3 terms. And this will now be represented by that point and that portion there, and that portion giving the final answer of positive 1. So we move on in substituting. In the next slide, basically we are substituting n equals 3. So you have y of n equals x of 0, h of 3, plus x of 1, h of 2, plus x of 2, h of 1, plus x of 3, h of 0. But again, in this scenario, you notice that the x values only go up to x of 2. Therefore, this will not be part of the equation. It's as good as you have a 0 here. And the next one, you have x of 2, you have h of 2, which are the maximum values. Therefore, however, again, in the next one, you don't have h of 3, so that term will not be there. This whole term will be will be basically not there. The only terms will be these two here, and the x of 1 is 1, h of 2 is 1, x of 2 is 2 times h of 1, which is 2, and then when you multiply and add the 2, you get a 5. Next, you substitute for n equals 4, you're going to have y of 4 equals x of 0, h of 4, plus x1, h of 3, plus x of 2, h of 2, plus x3 times h of 1, plus x of 4, h of 0. Again here, the last two terms here are not valid because we don't have x of 3 in the x of n sequence. We also don't have x of 4. And then you also notice that we don't have h of 3. The highest value for the h of n sequence is h of 2. We also don't have h of 4. So again, these two will not be part of the final solutions, but we have x of 2, it's a valid one, and h of 2 are valid. Therefore, when you multiply these two, which is basically 2 times 1 here, and you get your 2. The next one is, we just try to extend further by making n equals 5, just to see if there is any valid combination. So you have y of 5 here, you have x of 0, h of 5, plus x of 1, h of 4, plus x of 2, h of 3, plus x of 3, h of 2. This one goes on, but again, as you can notice, we don't have x of 3, we don't have h of 3, we don't have h of 4, we don't have h of 5. Therefore, all these here are invalid, and they basically give a 0. Therefore, the moment you reach that position, it means n equals 5 is not valid. You basically end at n equals 4. So when we now combine, to find the final answer now is basically y of n is basically just pick the value at n equals 0, which is this one, and this is the value at n equals 1, the value at n equals 2, the value at n equals 3, and the value at n equals 4. So that basically forms the final answer. Let's move on and now look at the next method. And this method is basically the tabular method. This method basically involves drawing a table of x of n and h of n sequences. We do a diagonal multiplication of the two sequences until we reach the end. And to illustrate this, let's solve the same example, finding the convolution of the two sequences, x of n, 3, 1, 2, and h of n, 3, 2, and 1. So this time now we're going to use the tabular method, and this is how you resolve it. In the tabular method, what you're going to do is, and I want you to watch this carefully, you have this part here consisting of x of n. So that part is for x of n. Then you have another part here, this part here consisting of h of n. Okay. And what I've done here is to put the sequences for x of n in that format. And then I've also put the sequence for h of n in that format. And then I've put a multiplication here, take note. And then what I'll be doing is now diagonally do a multiplication. What I do is 3 times 3, the answer is 9. So I multiply these two, I get a 9. Then I multiply again the 3 times 2, I get a 6. The same 3 times 1, I get a 3. Then I come here, 1 multiplied by 3, I get a 3. Then 1 multiplied by 2, I get a 2. Then 1 multiplied by 1, I get a 1. Then I come to the last one, 2 multiplied by 3, I get a 6. Then 2 multiplied by 2, I get a 4. Then again, 2 multiplied by 1, I get 2. Then once I get these products in this box here, you look at this box here. Once I get these products, then I draw the lines for the first one. So when you draw the line on that box, you get the first solution, which is 9, and that is a 9 here. And then I go to the next one, I draw a line like that, then add the numbers on top. 3 plus 6, you get the second sequence. Then I come here again and draw a diagonal line like that. Then add the numbers above, 6 plus 2, which is 8, plus 3, you get your 11 there. Next one is, again, draw a line down like that. Then add the numbers above, 4 plus 1, and that's how we get a 5 here. And the last one is as good as you've drawn a diagonal, similar to the way we did in the 9. Then you get the number above it, which is basically 2. So basically, that's how you resolve the convolution of 2 discrete signals using tabular methods. Let's move on to the next method. And the next method uses Z-transform. You recall in lecture number 8, I did mention that we'll be applying Z-transform in solving the convolution of 2 signals. And so this is a part where we are applying them. And basically, it involves the following steps. Number 1, take the Z-transform of X of n and H of n. Number 2, multiply the Z-transform of the 2 signals. And number 3, take the inverse Z-transform of the product. And then once you do that, you will have the output Y of n. So let us use the same example now to illustrate how we can apply Z-transform in convolving 2 signals. Okay, so in the example we've just been looking at above, we notice that Z-transform by definition is given by x of z summation from n equals minus infinite to positive infinite, x of n z to the power minus 1. That's for the first signal. Then you also do the Z-transform of the second signal, h of z. Again, summation from minus infinite to positive infinite, h of n z to the power minus 1. And once you found the Z-transform of the 2 signals, which is basically shown here for the first signal, x of z. This is the Z-transform. The second signal, this should have been h of z, not x of z. So take note, for the h of z here, it will be simply 3 plus 2 z minus 1 plus z to the power minus 2 if you apply that equation there. So once you found these 2 transform of the 2 signals, x of z as well as h of z, the next step is to multiply the Z-transform of the 2 in order for you to get Y of z. And this is what we have done here. This is a Z-transform of x of z being multiplied by the Z-transform of h of z. And what we are going to get here is when you multiply and simplify this, you are going to get an equation of this nature. Now this equation is of Y of z, but remember our interest is to find Y of n. Therefore, to find Y of n, all we do is now to find the inverse Z transform of Y of z, which will basically be a sequence now similar to 9, again 9, this one comes to 11. Okay, the 5 here becomes just, basically you just take the coefficients of this, and then you have 2 here, and then you close. So you will notice that this solution is similar to what we got under analytical method, similar to what we got under tabular method, and here we have it now even under Z transform. Okay, so having looked at this, let's now look at a tutorial. I've given a tutorial for you to try using analytical method, using Z transform method, and using tabular method. This must be really easy, especially after going through my presentation and my slides as given here. And then this marks the end of the lecture, but I've given a few references for you to check out and to try even more questions under this course.